Hello everyone and welcome back to my sp2 channel. This video is all about multiple bonds. There's going to be a little introduction about that, and then we're going to be looking at the bond formation in ethene and ethine molecules, and then I do have a very nice conclusion for you at the end. Okay, so starting by our introduction. In all the covalent bonds that we have considered so far, the electron density is concentrated along the line that is connecting the two nuclei, which is known as our inner nuclear axis. When the overlap region lies directly along this axis, it is forming a type of covalent bond that we call it a sigma bond. And you have seen many examples of that before. For example, the overlap of the two s orbitals in our hydrogen molecule, the overlap of an hydrogen 1s orbital and a chlorine 3p orbital. That's what we have in HCl. Or maybe the head-to-head overlap of the p orbitals that are forming chlorine gas, right? Or even the overlap of an, fluorine p orbital and beryllium sp hybrid orbital that are making the bonds in our BeF2, right? So these are all examples of, typical sigma bonds. Okay, now follow me on the next page. Okay, so to describe the multiple bonds, we need to consider a second type of covalent bond, which is resulting from side-by-side overlap of the two p orbitals oriented perpendicular to the inner nuclear axis. This is what we call the pi bond, right? So in a pi bond, the electron density is going to be concentrated above and below the inner nuclear axis, right? For the sigma bond, it was along the axis, but this is going to be above and below that, right? Now, because the orbital overlap in a pi bond is kind of side on rather than end on, it is generally speaking less effective, making your pi bonds weaker than sigma bonds. Okay, I hope that makes sense. Okay, now we're going to be looking at a couple of examples, starting by ethene, which is a very simple molecule. We have C2H4, right? And we know that there's a double bond in this molecule. So we'll try to understand the formation of the double bond here, okay? Now, if you look at the picture that we have at the bottom of the slide, you've got the ball and a stick model. And as you can see, we have 3 bond angles around the carbon, which is about 120 degrees. And that means we are looking at an sp2 hybrid orbitals, right, from carbon. And these are the ones that are using, right, that are being used to form the sigma bonds with the 2 hydrogen atoms and 1 carbon, right? So that is going to be for our sigma bonds. Now, after we're done with hybridization, right, after we're done with the sp2, one of the p orbitals is still going to be remaining as the unhybridized 2p orbital, right? So this remaining orbital is going to be always oriented perpendicular to the plane of the sp2 molecule. And these unhybridized p orbitals are the ones that are going to have the side-by-side overlap. And that's how we can form the pi bond between the 2 carbon atoms. Okay. Now, more about that on the next page with a little bit more, visual presentation. Okay, so as we said, we are going to have the sp2 orbital on the carbon that is going to overlap with the sp2 orbital of another carbon. That's how we make the CC bond, which is presented on the first picture, right? We're referring to this bond over here. And then the other sp2 orbitals are going to make 2 other sigma bonds, right, with the 1s orbital of hydrogens. So up to this point, we're done with all the sigma bonds. If you count your electrons, we have 10 of the 12 valence electrons that have been used to make these 5 sigma bonds, right? Now, the remaining 2 electrons that are in your p orbitals are now going to have the side-by-side overlap, as you can see on the third picture, and that's how you can make your pi bond, right? So in summary, if you have a CC double bond, that means we have the first bond as a sigma bond, and then the second one is going to be our pi bond, okay? So this structure actually explains why all 6 atoms in ethene are going to be on the same plane, and the p orbitals that can only effectively overlap if the molecule is a planar molecule, right? Also, a little bit about the distance between the two carbon atoms. When you're looking at the pi bond, we are expecting to get a shorter distance between the two carbon. The length is about 134 picometer. If you compare that with the CC single bond, which is 154, we're expecting to get shorter distance, right? Because that is in a stronger bond, so the two carbon atoms are closer to each other, right? Also, the molecule is going to be a little bit more rigid because of this pi bond, okay? Cool, cool. So that's about the double bond. Now, looking at the next page. Okay, now we're going to be looking at a thine molecule, which is C2H2. And this molecule is the one that has the CC triple bond. Okay, so what happened here is in this linear molecule, each carbon uses sp hybrid orbitals to form sigma bond, right, with the other carbon as well as the hydrogens, right, as you can see here. Now, each carbon has two unhybridized 2p orbitals oriented perpendicular to one another, as well as to the axis of the sp orbitals. These 2p orbitals on each carbon are going to have overlapping sidewise, right? We can say side by side to form the two pi bonds. So one of them is over here and the other one is over here, right? So in summary, we're going to have a CC triple bond that is consisting of one sigma bond, and I have two pi bonds. Okay, excellent. So based on the examples that we have explored together, we can draw the following general conclusions for using the hybrid orbitals to describe the molecular structures. So each bond is going to be equivalent of the two shared electrons. For the sigma bonds, always localized between the two atoms, shaped by the molecular geometry, and the pi bonds are going to be formed when we have multiple electron pairs that are being shared, right? The electron density always lies above and below the bond axis. Okay, cool, cool. Thank you very much for watching this video. If you like it, give it a thumbs up. There's going to be a lot more coming up soon. Take care of yourself, and I'll see you soon on the next video. Bye-bye for now.